Microphone is working, sorry, second presentation in English. I would like to start just introducing myself. I am Christian Dampierre, I'm the team leader for the senior design engineer in the WICONA project service. And now, everything is red, we are in the cinema, but it's not Deadpool, sorry for that. But my presentation will be quite technical, then sorry if some of the parts are a bit not used to your work. I would like us first to introduce what is doing my department, that is the project service, and we are designing worldwide technical solution for buildings and customized solution for element facade or stick wall facade in the building industry. Our department is working actively with each local units. That means we are able to make a global have a global overview of the developments, but also having a local view for what is needed in each country, working side by side with each technician locally in the organization. In the team, we are collecting more or less 300 years of experience in the business. If we are collecting all the experience of all the employers, and of course, being part of the R&D of WICONA, we can also have the opportunity to use solutions that are not developed yet or officialized in the market before then other colleagues. This is our daily business. Here you can see some nice building in US, in Norway. Some of them is in, for example, this one in London. And I could easily make a slideshow, a carousel of pictures of building, but I would like also to go a bit more in detail in some project that we have done. And but before, I would like to talk about sustainability. That is an important topic. Before, we were watching 37%. In my presentation is 39%. Important is that 1/3 of the global emission are because of our business. And normally it was before divided in 28% and 72%. 72% for the usage of the buildings and 28% related to the production of the materials used to build the building itself. Now, with all the improvements we have also seen before, more or less we are now having 50% of the usage consumption and then 50% on the material side. Here I have two different projects. This one is the Office of Environment and Energy in Basel in Switzerland, where we have done a nice closed cavity solution, super well thermal performing, U value 0.5, sound insulation 58 decibel, a super nice development, I would say, and solar panel on the rest of the building to try to save some energy and produce some clean energy for the building. And on the other side, we have 2 Trafalgar Way, a project that I will explain a bit more in detail later on. That is a passive house building for the cold temperature. That means the solution we have developed is for 0.6 watt per square meter Kelvin. And both of them are exactly the part related to the 50% of the usage of the building, and of course improving the performance and the thermal transmission of the systems. We are reducing this value. But then on the other side, we have also to take care of the materials we are using. And we, as WICONA, have decided to use our Circle 75 Air. That is, as you can see here, a low emission aluminium. And we have decided for all the standard series that we are selling worldwide to use our low carbon aluminium for that reason. Then we are trying to do our part in this side, and I believe also from the other side, I would invite you to also support us on that. Then I'm starting show you a couple of projects. On the top side, you can see the tonnage of the project. Okay, tonnage, it means tons of aluminium we have done for this project. And based on the value you have seen in the slide before, you can evaluate if it's better to use circal with us or go for a normal aluminium, and doing some calculation for that. This is the first building, is Al-Asima Tower, is in Kuwait City, is a 310-meter high building, and 55 square meter of facade, and we are not including the part of the podium below. That is not the case of today, but it was also done by us. Here we have some rendering for the building and some important information. As you know, the floor deflection has a main impact in the design of the system. And for this element facade, we were considering plus minus 19 millimeter. That means our joint between the two elements has to allow this kind of movements. And we had plus minus 4 millimeter for lateral movements of the element, and a high wind load of 6,000 Pascal. That multiplied for safety factor 1.5 makes 9,000 Pascal for the test in the test center. And then we had the lamella applied on each element with the lateral wind load of 1,700 Pascal and in and out corner. And all of that was to be tested based on American standard. That is normally almost 2 times more water than the European normal standard. We have 2 liters per square meter. In the American standard, we are around 3.5. This is the shape of the building, and as first step, I was recognizing that we had some curved elements and with different radius. In the outer radius on that part was possible to find a solution for a polygonal situation where we can play with our gasket shape in order to have straight elements, but it looks like that they are curved. On the other side, we have done bended solution element for that. And then we have recognized that there were 2 nice corners. I was going to watch a bit more in detail the corners, and I have recognized at that point that also in the corner area we had a lamella that is taking lateral load. And I've recognized that in the initial design there was only considered to have a mullion profile in that area and no other mullion profiles. And that was quite challenging for structural point of view, but spoiler, at the end of the project we have decided to split the element like that, also because it was not physically possible to install such a big corner in the concrete with that shape. Then the first point we were watching deeply into are the movements and the standard requirements for the American standard. Our gasket system, we know that has been tested already for American standard and also for the CWCT for UK. That is more or less similar. And then for the development of the system, it was for me important to start think about the tightness of the facade. And then the only point was to check if we are able to manage the plus minus 19 millimeter movements that are quite high. And then we have decided to use our normal approach for element facade. That is this one that is in the video. The element above is engaging the gasket that are continuously installed on the line below. Okay. Here looks like the gaskets are quite weak, but in reality are quite stiff. And when during the installation, they are remaining quite straight. And it's really quite easy for elements also 2 meter bright to install the gasket in the proper way. Just because sometimes I am having some request how to check if the middle gasket is well installed and is well engaged. The gasket has also the flexibility from inside to be open and check manually just if the installation has been done properly. And we know that this gasket system can allow then this 19 millimeter. And we know also that we can apply our drainage principle, that normally we are going to drain also the area between the internal and the middle gasket that normally should be tight and is tight. But during the installation on site is happening a lot of times that is raining and the water is stacking in that area, and then it's really difficult to get that area dry after. Then with our principle, we are always draining vertically in order to avoid the water to come up into the system. And outside we have a foam part that is able to be compressed and is also draining out the water. Then the second topic I have to check for the development of the system was were the reinforcements for the wind load and static. And here we have a couple of choices. Or we are going to increase the depth of the profile, easy way, or we are going to increase the thickness on the back of the profile, also possible, or we are going to apply some reinforcement profile. And this has also to take in consideration the lamella applied to outside and avoid that the profile is twisting, and then the solution is still stable. And only at that time, we had the possibility to verify how to apply the SG on that, because the project was SG constructed. And more or less at that point, I have shown you how it works, our gasket system, and how we have done technically a solution starting from a standard system, something that we know, something that we are normally using worldwide. This is the tower, some picture of the tower finished. And now I would like to jump in the next one. This is a project in Gatineau, in the area of Ottawa, in Canada. Is 600 tons, and it's a quite big building. It's a renovation building, and renovation building is for us really important, because then it means it's connected always with the CO2 emission and the discussion the topic I was speaking before. And here also some information, and if you recognize here, the movement are much bigger. We have a plus 30 millimeter and plus 35 and minus 30 millimeter, and that means that my joint between the two elements must have the flexibility to move 65 millimeter, and that's really a lot. Then on the other side, we had also seismic movements, and all the building were supposed to be tested for interstory drift and safety seismic test based on American standard. And this was the request we have received at the beginning. That's a male-female system that, of course, is not aligned with what I have already shown you last time in the last project, because we are normally using female-female system that is only the same profile all around the element. That means we have only one profile and our gasket system that is compensating the movements. Here, in this example, we have the green one that is the male part and the red one that is the female part, and based on the movements, they are moving and deflecting together with the building. And how to transform this one in that one? Because at the end is that I know how my gasket system works, and I have to find the right way to have a nice approach for the architect, for the customer, and that is performing properly. One thing I have to take in consideration is that we are always using 3 layers of gasket. The 3 layers of gasket are giving us the possibility to have outside the rain screen, that means the direct rain on the elements are blocked completely from that. The middle gasket is the one that is watertight, and then the internal gasket is the one that, in our opinion, has to take care of the airtightness. That is the one also that you can take care from inside of the building after the installation. But then if I'm transforming my solution into a male-female approach, then you see where the green arrow is. There I need much more space, because my element has to move up 35 millimeter and down 30 millimeter. And that means I need also to increase the depth of this profile. That means for sure more aluminum. That means for sure much more emission. Sorry. But I cannot do anything else. And then at the end, this visual part of the profile, it will be bigger. And here in Europe, a lot of times we have the stack joint in the floor part that is completely hidden in the building from inside. But in US, in a lot of cases, we have more or less at 800 millimeter from the floor level. And that means it's quite high profile to see. That's the disadvantage. Then we had here 38 test sequence to run. Is always the same water tightness, dynamic, static, sucking from inside, and I believe he is practical with this topic, knows that. But 38 times were really a lot. This is the mock-up that we have done in the test center for testing, and we have tested the joint completely open at 80% of the maximum design opening. We have tested the element with the interstory drift, and both of them together. And at the end, we did also the test for the seismic test. Now, here, a video of the installation sequence, where the element is engaged on the side and just sitting on the male-female solution. Here in the middle, the video of the American standard water test, that you will recognize the amount of water. If you are used to see the European test, then here is really a lot of water. And on the left side, the seismic test, and the aim of the seismic test was to have plus minus 30 millimeter movements. At the end, we reached plus minus 75 millimeter because the test center has recognized that nothing was breaking, and they tried to play a bit with our sample and reaching the limit that they can test with the machine. And at the end, the only thing was just removing was a visual gasket that you can see on the top of the video of the yellow panels. That was only visual, no technical needs, and important for the test was to avoid everything to fall down and create problems. I have no picture of that building because it's currently in installation phase. And of course, if we have some nice picture of that, we will share that on our social media channels. Then here, 800 tons to Trafalgar Way is the project I was discussing, I was showing before in the slide. It's a passive house project and is here based on CWCT test for UK market and passive house also test for cold temperature. Here the movements, now you have learned how it works, our system. We are around plus minus 19 as the first project I was showing you. That means it's not a problem for us. And what was a bit challenging for us was the type of elements. We had straight facade, polygonal facade, and curved facade that I was already showing you a bit how to handle that in the first project I show you. But one of the most difficult parts were to take care of the thermal insulation, because the passive house certification is requiring really high performances. And then we have verified in all the three positions in the plus minus 18 and 19 millimeter that the thermal performance of the system was in a range that can be always the same. And then we have recognized that in this area, to try to reach that value from our standard application, we had to make some improvements. And then we had at the end defined some particular gasket able to be flexible in that area and able to reduce the movement of the air in that marked area. And then for the polygonal system, we were just thinking to play with our gaskets, the internal one and the middle one, and use some kind of adapter profile to have the possibility to use same elements, build the same elements, and add or remove the adapter profile. And here we have prepared for our customer a nice overview for each corner, which kind of solution to be used into the project. The project was quite big, and then we had really a lot of different corners. Here's some picture from the test in Vinci in UK. Here the bended, the curved element, and of course the dynamic test with the propeller. Here the last project. This is Paris Park, is a project in Paris, and it's like a nice diamond in the middle of the city. It's 350 tons, and the nice part of this design is that if you can see this surface in the top corner, they moved to inside completely the structure, and that means each vertical line you see is going for after each line 0.6 degree more inclined to the other. And that means the shape of the building is going completely down on that side. And to find a way to solve this solution, we have developed 5 different set of profiles that are compatible between them. And we are then allowed to mix the different profiles we have done, the different system we have done. And unfortunately, here I cannot show you the section of our standard system because this has been completely developed as new. There was no reference, there was no starting point. We were doing pure engineering to find a way to make this situation work. Then what is happening is that at the beginning of at the starting point of the building, all the elements are starting at the 0 point, but then at the top of the building, each line of elements are moving inside, with a difference also between 300 millimeter from one side and the other. And then that part on the top, where you can see the red and blue line, we're getting a bit of thermal bridging, because we had to find a way to solve the thermal part of this situation. On the outer side, the right part of the elements were getting completely exposed, if you can see this part here, from outside. And we had to avoid the air to make a thermal bridge, or also the temperature to come inside to the building. Another point we have recognized is that all the stack joints were inclined. And that means that if you are going inclined, one element next to the other, they have a different outer line or inner view of the building. Then what we have done, we have transformed all the stack joint horizontally, in order to have from outside always the same line, from inside always the same view. And of course, it's getting a bit more challenging for the customer, for the metal builder, to screw the profile in a proper way, but at the end was easily done. And as you can see here, this is only the rendering. The wish of the architect was to have all the stack joint in the same position. And then here we can easily recognize that what we have done at the end, also with different inclination, we were always keeping the same stack joint. Here's some picture of the test done in July in Italy from the metal builder. The air permeability and the water tightness are based on European standard, also the impact test resistance. And I think that's all. I think this presentation was a bit technical, a bit too much maybe, but that's my daily work. I hope just that you can just quickly recognize that all the projects I was showing you are more or less 220 tons, 2,200 tons of aluminium. And then for projects like that, make the right choice with the right aluminium is making the difference. Okay, thank you very much.